1 plus 1 plus 1. This again is 1 plus 1 plus 1 plus 1 plus 1 equals 8. And then you divided it by the number of these components, that's 8, and you get 1. And similarly, if it was a minus 1, you would have got minus 1 there. Okay? So we're not going to go through the whole thing. But the magic of this is that's of course what we saw is fairly trivial. If you think about it, you send things appropriately. The magic is that when a bunch of users are using this wire, okay, if a bunch of people are using it, then when multiple senders send, you'll get the signal can go to 2. Okay, one person sends a 1, and that gets if at the same time another person sends a 1, this is simple addition of voltages. Okay, so it becomes 2. So if you had 3 users, if everybody sent 1 at the same time, you could go up to 3, 4, and so on. But when you receive it, you still apply the same formula. No matter what is coming on a wire, it's a jumble from 4 different hosts, but you multiply each component with the code of 1. So this is A, this may be B, and at the receiver, you component-wise, you multiply by A's code and divide by 8, and you will get 1 or a minus 1 depending on what was sent. And what was sent by the other 16 people doesn't matter. Okay? It just gets filtered out. Okay? So it's not going to work if you arbitrarily pick codes. The codes have to be picked carefully, but it does work for selected sets of codes. Okay? So this is an example where 2 different people are sending with different codes, and then adds up to 2's and minus 2's, and then when you receive it, you right. So at every point, why? In case you're wondering, why do you get 2's and minus 2's and nothing in between? At every point, one person sends a 1 or a minus 1. The other party sends a 1 or a minus 1. Okay. If you sum them up, you either get 0, 2, or minus 2. Okay. So you get zeros also. So these are all zeros, but there's no 1's and minus 1's just because the additions of 1 or minus 1 with 1 or minus 1 will give you 0 or 2 or minus 2. Okay. And then any questions? CDMA. So CDMA is, well, it was used for a lot of things. I think its roots are in Second World War, where they were using for communication across the continent. Sort of encoded some kind of an encrypted communication, and but today it's used in a lot of wireless networks, including a lot of cell phone networks. Okay. So let's see. Okay, let's get started a little bit. We're going to distinguish our discussion between wireless local area networks, where you have your computers, laptops, and over here, for example, you can connect to the university network. Those technologies are very different from wide area networks, basically cell phone based networks. So we start with some discussion of local area networks. The various protocols that you use for wireless communication at the link layer level happen to start with 802.11. That's the standard that IEEE picked for wireless communication. But then there's various siblings of that standard, and they get names like A, B, G, and so on. So probably the most widespread right now is 802.11b. It uses 2.4 to 5 gigahertz spectrum, 11 Mbps maximum, uses something called DSSS spread. It's kind of like it's a variation of CDMA that we talked about. It's very common. Technology is coming up, maybe already in operation, is 802.11a, which is 54 megabits per second, uses 5 to 6 gigahertz spectrum. 802.11g, again 54 megabits per second, but in a different frequency range. Okay. So what do they have in common? They all have base station and ad hoc network versions. So you can have this infrastructure mode, or you can just have a few laptops talk to each other with any one of those technologies. And all of them are based on CSMA CA. So CSMA is carrier sense multiple access. CA is collision avoidance versus collision detection. That was the wired Ethernet technology was collision detection. Okay. So we've already seen this, the concept of base station, and there's a concept of a cell. Okay. So a cell consists of an access point and a bunch of hosts that can communicate with each other. Okay, so cell is another name, also a basic service set. So 802.11b, the spectrum is divided into 11 channels based on frequencies, and the administrator can choose, access point administrator can choose which frequency to use. And of course, interference is possible. To get into a network, a host has to associate with an access point. So as that happens when you turn on a wireless laptop or something, it scans the channels, listening for specific frames and containing the access point's name and MAC address. Is there an access point that's willing to talk to me? And the host will pick one, associate with an access point, and generally there will be some kind of an authentication. If once you try to talk to the access point might ask you for a user ID password or something. And once you're associated, you're part of the network, you generally run DHCP. For a normal laptop, you have to have an IP address, and when you're in a wireless network, usually it's not a fixed IP. As you associate with an access point and become part of its cell, you get an IP address, a dynamic IP address. Okay. So one question is, why do you use CSMA? CSMA basically means that you do not transmit until you find the channel empty. And CSMA CD is an extension of that we use for wireless networks, where of course, you still do not send so long as the channel is used by somebody else. But you also, if you send, you look for collisions and resend if there was a collision. And that part is completely taken out in the wireless Ethernet. So IEEE 802.11 is also wireless Ethernet. Okay. So now the question is, why do we want to change things? Why don't we have collision detection? It seems to work pretty well on a wired network. And the reason is it's much more difficult to detect collisions in a wireless world than a wired world. So one is a basic engineering reason that the way the wireless nodes are designed, many times you cannot transmit and receive at the same time. Okay, you either transmit or you receive. So clearly, if you're transmitting, somebody else is transmitting, and then you start receiving, and nobody is transmitting because they're done transmitting too, right? So that is one reason you don't have collision detection as part of the wireless Ethernet. So the second is this. What is this problem? Hidden terminal problem and fading problem. So it's possible, one more time, that A talks to B and C talks to B, and C and A cannot hear each other. Okay. Because again, for two reasons we already discussed, distance or this thing. And if your protocol is based on collision detection, okay, it's not